everybody, I'm Professor Adam Teman of the EnICS Labs at Bar-Ilan University. And today I'm going to show you a short overview of how I set up a project workspace. So first of all, why do we do this? What is the motivation for it? And it's really important to have an organization methodology for managing a project, like how we kind of structure our files and so forth. When we download a Git repo, where everything is going to be so we can have version control and so forth. So everybody knows where to find things and has some sort of logic in where things are stored. So this is the methodology I set up. And we'll start with a base directory, which I'm going to call project root over here. Of course, it will have the name of whatever our project is called. And if I clone something from my Git, that's going to be the name of the folder that is downloaded, and everything's going to be underneath it. So the first and most important kind of folder that we're going to talk about is called Workspace. And I have a specific folder where we're going to run all our tools from. All of the different tools are going to be run in the Workspace. So we're going to do CD to the Workspace, and everything is going to be relative to it. Why do I do this? Well, there are a few reasons, and I'll talk about a few of them right here. So we have one directory where we're going to run all our tools from. So it doesn't matter if we're doing simulation, if we're doing synthesis, if we're doing place and route, everything we're going to run from this workspace folder. We know we don't have a different workspace for everything. It's really easy to access everything from there. We reference everything, therefore, one level up. So we're inside the workspace, and then we do source ... and something that we're going to be discussing in the next few slides. So everything is one workspace up from there. That means that under the workspace is only things that we actually created during this run. Nothing that is basic to our project root, nothing that we actually downloaded from our, that we cloned from our Git is going to be under this workspace. And that means that we can easily clean everything up by just removing all the files that are down here. We made a run, we didn't like the run, we want to get rid of everything that was there. We can do something crazy like rm-rf workspace star. So we just clean up everything below here, and we don't risk deleting anything that was basic to our whole project. And it's also easy to create parallel runs without clutter. So sometimes we have a run and it came out good, or we want to make two runs at the same time in parallel that are running on a bit different files or a different something. So we can just make another workspace. We can call it workspace 2 or something else that will be parallel to this. And each of these workspaces is when we did a separate run of our tools. And since really there's nothing essential inside this workspace folder, everything is products of our run, log files and so forth and so on, we can do that, and it doesn't, we don't lose anything that way. So that's why I have a separate workspace that is parallel to all the other folders that we're going to show now.
So I'm going to open a terminal over here, and the first thing I'm going to do is I'm going to go into the area where I'm going to work. In this case, it's called full sock example. And what I'm going to do is I'm going to open VS Code. I like using VS Code as an interface. You don't have to. You can use any other type of a interface you want, or just the general command line in the terminal. But I'm going to show you these things on VS Code because it's kind of nice to look at. So then what I'm going to do is I'm going to go File, Open Folder, and the folder I'm going to open is this full sock example. And that provides me with the interface I see over here. And as you can see here, I have the different types of folders that I discussed beforehand. And so we're going to go over them now. So the initial folder that we're going to be discussing is the Workspace folder. So I can go CD Workspace, and everything I'm going to do is going to be from this Workspace folder. And if I look at this Workspace folder, I can see that I have a whole bunch of stuff. This is from some previous run that I ran over here, and I'm purposely not going to erase it right now. But in general, what I could just do is do some sort of rm-rf star on this directory, make sure you're in the right directory, and I can remove everything and start over when I want to start a new project or something. I can also create another workspace called, let's say, Workspace 2 that is parallel to this, and I'm always going to run all my tools from right in this Workspace folder.
The next folder is the source code folder, and that's where I put all of our RTL files. So we have this source code folder that's going to be parallel to the workspace folder under the project root. And inside, I'm going to divide my whole design into two things. One is called the RTL folder, and the other is the test bench folder. The RTL folder will have all my DUT, all my design files. The TB will have all the test bench files. So everything I'm going to synthesize and so forth will be in here, and this is going to be used for simulation and so forth. You can go and add other subdirectories and files. You may have, for example, and we'll see that later on, that there is a list of files inside the source code folder which tells us what files to run during simulation, what files to run during synthesis, and so forth. So I'm going to usually keep that in the root source code folder.
So the next folder I'm going to be discussing is the source code folder. And in the source code folder, I have my RTL and my test bench. And as you can see in my RTL, I have several subdirectories that have different parts of my RTL however I wrote it. And then I also have a test bench directory that will have my test bench and so forth inside it. I may have all kinds of other types of files here. For example, in my source code folder, right here, I have this RISC-V source list file, and this has a list of all the files that I'm going to need to read in to be able to read my my Verilog, which I will do later. I may have different types of files, like if I have different test benches, and this is under my test bench folder, I may have different types of test bench files in here and different files that will help me, again, have a list of files that I can read for different types of tests I want to run. So that we'll be discussing later on when we discuss things like RTL simulation and so forth. But as you can see, I store all of the Verilog code or system Verilog code or whatever my HDL is underneath the source code folder with a bunch of files that may help me to access the right files for each step of my work.
Then we go on into what we call the inputs folder. And the inputs folder has all the files you need to feed your tools with. This is design definitions, SDC files, all kinds of things like that. I'm going to detail that a little bit in a second. So many of them are shared between tools. For example, when we do synthesis or we do place and route, we want to have the same SDC file. And so they're all in this same root folder called inputs. And we can, depending on what we're running from the workspace, we can just address them by going, /inputs and whatever the file is. So what do we have in here? Some of the files that we'll have in here are top level defines, which is all the basic project definitions. The reason I have it top level here in kind of triangular parentheses is because all of these files are specific to our design. We need to edit all of them. And so when I download this, when I clone it from the Git, I keep a generic name that I want to change to my project name to make sure that I have actually gone and edited these files, and I don't expect them to be something that comes straight out of the Git repository to generic to everyone. So that's why I really use the top level name, so I don't accidentally copy this to a different project and expect it to all work nicely. Okay, so the defines is all the project definitions, which I'll be discussing soon. There's the SDC file, which is usually the design constraints that's used by synthesis, place and route, and so forth. The MMMC files is the multi-mode, multi-corner, which are going to be used in both synthesis and place and route. There are CPF for low power design. There's CCOpt for directing the clock tree. There's the floor plan defines, which are things that I'm going to be using to make my floor plan. There are different things like that. IO files, how I'm going to put my IOs. So these are different things that are going to be input to the tools that I'm using. And so I put them inside this inputs folder. However, I just want to note again that these files, what you're going to download from a Git or something, is going to be some sort of a framework for a file, but you're really going to have to customize these according to your specific flow.
So the next folder I'm going to go to is my inputs folder. And inside my inputs folder, you can see that I have several different types of inputs. And in this case, my top level name is LP RISC-V top, and that's why all of these files are called LP RISC-V top dot something. The reason I don't give it just a generic name is that each of these files has to be customized for my particular design that I'm running. So I may download some sort of a skeleton from my Git repo or something like that, and I want to make sure that I do go in and edit all of these files very definitely before I start using them. So I purposely, methodologically, called them with not a generic name like toplevel.sdc, but giving it the design name. And that way I make sure that if I get an error there, it means that I didn't yet open this file and start editing it, and maybe it will do all kinds of bad stuff. So it's also, I can't just take these files from one project to another. I have to really work on them. So that's why I decided to give them a distinct name. So what kind of files do I have here? I have all the different files that we discussed a second ago. So I have the defines file over here. I have the SDC file, the MMMC definition file, CCOP definition file, floor plan definition file. I have an IO ring file. I have a little README that kind of explains what to do over here. So these are the different files I have in my inputs. They're going to be particular for my design. So I have to go and edit all of these and prepare them for my particular design.
The next folder is, on the contrary to that, is the libraries folder, which we're not going to really customize at all. That's going to be provided by our CAD or EDA team, and it's going to have all the paths and the file names and specific things, definitions for a certain process or library. So most of the stuff over here we're going to prepare for one single, PDK or standard cell library or whatever, and for different IPs that we're going to use, and we're going to stick them all under this libraries. So we're going to be able to pass them between different projects, and they already have all the data that I need to run a flow in that given process and with those given IPs. So what are the things that we have inside? Well, some of them are these libraries process. This is usually going to be the process name or something like that, which is going to have all kinds of technology info from the PDK that's not specific to like the standard cell library or some sort of IP, like the tech left, the extraction data, stuff like that. Libraries.standardcell, whatever the standard cell library name is going to have specific info about the standard cell library, like where the lefts are, the libs are, which cells to use for different things, and so forth. The libraries.io is going to have stuff about the IO library that I'm going to use, such as the lefts and libs and specific relevant commands and so forth. And we also have one that's called libraries.sram, so I'm going to be compiling my SRAM cuts that I want to use. So this I'm going to really have to be filled out and customized by the user, but it's going to point to the different paths where I have compiled my SRAMs and what SRAMs I'm going to use and what their different data is.
So next we're going to talk about the libraries folder, and in the libraries folder I have particular files for each of the different types of libraries that I want to add here. So I have a general one for the basic PDK that I'm using, and this is going to be TSMC65LP in this part, and it tells me different things about it, like the metal stack and other types of things. I have, for the standard cells over here, a tickle file, a .f file for simulation. I have one about the SRAMs if I'm going to be using any SRAMs in my design. I have about the IOs for both the tickle files for my backend flow and the .f file for my simulation flow, and all kinds of other things that I would need here that are particular to my specific design process and my particular libraries that I'm using.
So we've arrived at the scripts folder, and the scripts folder is really the root that has all the scripts that are needed for running each tool. Okay, we provide a basic script for each tool and stage, but they need a lot of editing and customization. So when you download the Git, you'll have all kinds of frameworks for how to run the flow, but you'll really need to customize this according to your specific project. What we're going to have here are scripts for each one of the stages, and they'll be described in the rest of the flow as we go. So just as examples, we have xrun options.rtl or .gtl, and these are options for running Xcelium simulation at the RTL and behavior level or at the gate level, and this is a kind of a script that can help us automate things. Then we have like Genus tickle is a synthesis script for running Genus step after step, and we have Innovus tickle, which is a place and route script for Innovus. And there are going to be many more of these scripts that are used for different parts of the flow.
So next I'm going over to my scripts folder, and in my scripts folder I have different script files that I showed you before that I discussed. So for example, xrun options.rtl has all the options I'm going to send to Xcelium for running an RTL simulation. I have the same for a gate level simulation and a power back annotation type of file. Then I have a file for my Genus synthesis run, my Innovus place and route run. I have general settings that I like to send to things and procedures that I wrote for doing all kinds of things. For simulating in Xrun, I have one for back annotation simulation, for a Voltus post-synthesis. So all of my scripts are here. These are going to be generic scripts that you're going to download from the repo. You may have to tweak them a bit, but they're going to be basically be sent from project to project, and you're going to do a limited number, at least at the beginning, of changes to these types of scripts.
The remaining folders that we have our apps, which is a place that we're going to be running all kinds of apps, different things when we do SOC simulation. We'll see that later on. Okay, reports is where we're going to dump all the reports during our flow. There are going to be subfolders here for the different stages, but all the reports will be accessed through this reports folder. And export is where all the products are going to be. Net lists, databases, GDSs, stuff like that. They're going to be under the export folder. And finally, we have a docs folder where we're going to put different documentation that will be useful and important for us to use during the flow.
So the other folders I have are the apps folder, which we're going to be discussing much later. The DBs is where I'm going to be saving all kinds of databases that come out of my my flow. And you see that these were created during the flow that I ran last time in this folder. My export is going to be the things that come out of my design at the end, the final net lists and so forth. And I have my reports file, which is going to have different types of reports at different stages, like a report timing over here, at different stages of my flow.
The next thing I wanted to discuss is the tickle arrays. So the flow that I created uses tickle arrays. I don't know how familiar you are with tickle arrays, but these are key value pairs. They're called in Perl hashes or in Python dictionaries. In Tickle, we call them arrays. And they're used for storing design and flow info. So I made a few basic arrays that are used, and they enable us to access all the different values and data that we need. So the basic one is $design. So we put $design and whatever the key is inside these parentheses. And there are many different keys in here. And it includes data about the specific design. So this is all custom for our specific design and not generic for any design. Okay, most of this is defined in the inputs top-level.defines file that we saw before. So what the design name is and all kinds of different things about it, what the clock name is and different things like that, they're going to be inside this design array. Then we have a paths array, which is going to have important paths in the Linux directory structure. And this makes it easy to kind of move our flow between different paths where our workspace actually is, or if we're on different servers and so forth. So this paths has all the basic definitions of how to reach a certain file or directory inside our Linux environment. Tech files is the actual files that are going to be used, getting to them through these paths. So there are files for defining the technology like lefs and libs and so forth. Most of these are defined in the libraries file. So again, most of them are going to be taken between different designs or different projects that are done with the same process, standard cell library, IP libraries, and so forth. But we're going to call them tech files. That is the array that is going to be used to access these different things. Finally, we have the tech array, and that's technology-specific values and parameters, like just the list of clock buffers that should be used, or the list of the names of the fillers that should be used, or different types of things like DRCs, or all kinds of things. We'll store them inside this tech thing. And again, this will be mainly for a specific library and can be migrated between different projects in the same library, but some of the stuff will be specific for our design. So we're going to use these four arrays quite substantially as kind of basic ways to access the different data we need. However, this becomes very complicated because different things like a tech file will actually be based on different paths that may be built up from several different stages. And it's really hard if we have a small typo in one of these things that to find out where the typo is, especially when in this type of EDA world, we have very long names of paths and file names and so forth. It's really hard to find out where we missed a certain letter or made an O instead of a 0 or something like that. So what we when we do this parameterization really and build things hierarchically, it becomes really hard to do it. So what I set up is something called the debug.txt file. And what it is, it's a file that we keep on writing out all the variables that we created in the scripts, and we write what their values are. And therefore we get this long text file that has the name of the variable and its content inside it. And therefore we can really go and search through this variable when our script breaks down, and this helps us improve the debugging speed.
So now I'm going to go into my inputs file and into my inputs folder and open up the defines file. And I want to show you that I'm using these tickle arrays. So we said that the design array has all kinds of things that are specific for my design. So for example, this full chip or macro key is going to be called full chip. That means that this run is running on a full chip of the design. So this is going to be an array that has a lot of different things about the design. It has something about what the name of the clock is, what the port of the clock is, and so forth. There's also a list of clocks and a list of ports for the clocks and what the periods of the clocks are and so forth. So this is going to be the design type of array, and I'm going to set that really inside my dot defines file inside my input. You see these all set things in this design array. One of the important things about the design array or all of these arrays is then I can pass to a function just this as a variable that goes by, and I don't have to pass each and every one of these sub variables. The minute I pass the array, I get all of its content, and so that really helps me make a clean workflow. Okay, when we said that we have things that are more about like the technology, so if I go into my libraries and I look at, for example, this standard cell library type of thing, I have the paths to where my standard cells are set up, and I have things that are in the tech array, which is just all kinds of things about the standard cell library itself. So we have all kinds of things, and then the files, so that's under tech files. And this is like, for example, where the technology left is and where all of the standard cell lefts are and so forth. So there's a lot of stuff in here that we're going to be discussing later, but really I use these arrays that are called tech and tech files and paths for setting up all of the access to the different things that I have in my, basically mainly in my standard cell libraries and my IP libraries and so forth, while for the inputs things, these are more stuff that has to do with the design itself, and so they're going to be mainly inside this design array. So now just taking a look at this debug.txt file. So you see there's this file over here called debug.txt. And where I'm going to actually make it is, so let's go look at the defines file. And if we scroll down to the end of the defines file, I see that there's this kind of cleanup code. It says print values into debug file, and it's going to go and use this EnICS print debug data command, which is inside my procedures.tickle script. So in the script in procedures.tickle, that's going to have this EnICS print debug data. It's going to be actually writing into this debug file. Okay, so what it's going to do, it's going to go over the different things that I asked it to go over here. It's going to write these variables that you can see up there, these variables and these dictionaries, these tickle arrays, and it's going to go and write them into this debug.txt file. What this provides me with in the end is inside my workspace, I have this debug.txt file, and it's just a dump file that helps me debug things. So I can see that any type of variable that I set, for example, where the path is to the standard cells that are high VT. So it's going to be over here in this type of a path, which is a real long path, and it may have been created by stacking up all kinds of hierarchical things and so forth. So this way I can actually get to it easily and use it for debugging. So any of the different types of variables that I set up, they're all going to be printed out here, and this really can help me debug things when I'm setting up when I get some sort of error when I'm running my scripts.